we start or we go ahead with the reading session of the paper. I wanted to go through section 3 today, optimization and quantum walks, and I think that was just really about, kind of setting up the basis for the paper. And I think they're going to talk about graph Laplacians, which I was curious about because I've never digged into. So let's see what we learn out of these. We begin by reviewing and establishing the notation for both quantum optimization and quantum walks. So these I also haven't touched in. So we'll Google that, as will be relevant to our narrative. The goal in optimization is to find the value z star such that f of z star is a maximum or a minimum of the value of the objective function f. Okay, yeah, that's just a way to define optimization. So you want to find a maximum or a minimum. For the most part, we'll restrict our discussion to classical functions fz, where the domain of z is a bit string of length n. Due to the simplicity, to mount the problem to n qubits. Throughout this work, we will use the notation x sub I, y sub I, and z sub I to refer to the Pauli operators acting on qubit I. While there is some interest in finding local minima of problems for practical reasons, the discussion in quantum optimization often focuses on the more challenging task of finding global optima. And in this case, can be concisely restated as Z star is arc mean. What is these actually? Is this official notation? What does arc mean? Arc max, arc mean. In mathematics, the arguments of the maxima, abbreviated argmax, are the points or elements of the domain of some function at which the function values are maximized. So argmax of fs this is actually a set. So this is all x where x belongs to s, and for all y, which also belong to s, the f of y is smaller or equal than f of x. So this is basically defining that x is okay, and s is being what? The argmax of some subset s of x. Okay, so s being a subset of the domain of the function. So this is just saying that this is a set. That's what we're gonna arc mean z of fz. Okay. These are all x. It's just it's a bit confusing that it's used in the notation here as well, f of x. But okay, in some cases, one is interested in the typical quality of solutions a method produces, which can be quantified by the approximation ratio. As a matter of clarification, the approximation ratio is in classical discrete optimization, and approximation methods has been defined differently than the approximation in reference to quantum optimization and QAUA in particular. We choose to take the convention common in the quantum literature, where an approximation ratio of 1 is perfect, 0 is failure. And we seek to maximize the approximation ratio, which is opposite to the convention taken in the classical optimization algorithm literature. Hence, for this choice of convention, we use throughout the approximation ratio for minimization of a solution z is defined as, and I guess this is expectation value, now I know. So f max is the maximum value of f. And the approximation ratio is evaluated over the distribution of solutions. So over the distribution of solutions a method produces. And or a distribution of instances for a problem. The approximation of solution z. So z star is sort of what we're aiming at. Z is what we're going to find, right? And so, but isn't that dangerous to do that? Isn't that like, cannot these be 0 actually? If this is the max, right? Or is this, what is this? Is distributions? is evaluated over the distribution of solutions a method produces. Is the maximum value of f. Yeah, I don't know if that actually is expectation value, but I get what they mean, right? So it's you want the ratio between. So one is perfect. This means that if this number in the numerator is the same as the one in the denominator, which is the perfect, then you have a 1. But is f max... Oh, that's arc mean, sorry. Okay, so we are defining it like as a minima. So the difference between the maximum of the function and the minimum of the function. So this won't ever be 0 unless f is just like a constant function, I guess. In which case that breaks, but whatever. Quantum annealing works. Okay, so quantum annealing works to solve this optimization problem through connection with the adiabatic principle by evolving under Hamiltonians of the form. Yeah. This is something to unpack. I don't know if I understand that. I definitely don't understand that. But when one begins in the initial state, yeah, that's. I mean, I understand the annealing, the adiabatic principle conceptually. So you start with the initial state that's just the plus state, and continuously varies the schedule function from S0 to S1. If this evolution is slow enough in a sense which can be made precise, the evolution stays in the ground state of the joint Hamiltonian and produces the optimal bit string Z star with high probability. We note that there is sometimes a subtle distinction in connotation between quantum annealing and the optimization through the quantum adiabatic principle, in that quantum annealers built from analog components sometimes operate without the ability to exactly give S0 equals 0 and hence approximate this path by making the coefficient of the transverse field large in comparison to the magnitude of fz in initial stages of the algorithm. So that's a combination of two Hamilton, like of these. I don't understand how this is formulated though, but initial stage. One can use a similar construction for functions with only one marked state, that is f of z equals 0 for all, but fz star equals -1 to formulate the Hamiltonian analog of Grover's algorithm, which traditionally proceeds via the Hamiltonian. Okay, where p plus is this super. What is these? Which was written in a way as to be structurally similar to the previous equation. I was gonna say that is just really similar. So it's basically. So what you're, I mean, yeah, kind of, right? Because Kroger's algorithm it looks like a bit like annealing, right? It's like you're evolving your state step by step, trying to get to that target state. At a glance, the two Hamiltonians appear quite different, and indeed, in many ways, they are. However, in the literature of continuous time quantum walks, it has been noted that there is a common structure that underlies the two, and it is this structure we will run with to develop intuition for quantum optimization of classical problems. In particular, both algorithms start from the state, the superposition, and perceive a Hamiltonian of the form where LG is the graph Laplacian of a graph G. Okay. Where the nodes are computational bit strings or basis states. Okay. A graph Laplacian, where the nodes are the computational bit strings or basis states. Indeed, it turns out that for a wide family of graphs G, the above algorithms would produce the ground state of fz, albeit with computational scalings that depend on the specifics of the graph. However, to date, the specifics of the graph have been underutilized in understanding and accelerating these algorithms. That starts to sound interesting. Let us briefly recall what we need to know about graph Laplacians in order to unify the conceptual features. Okay, so you're saying, so there's some sort of graph you can represent this in, so you can represent an operator. Is this going to be an operator, or is this a state? I don't know. Okay, so at a conceptual level, the graph Laplacian is the real space Laplacian used in... Is this pronounced Laplacian, by the way? So... I thought there'd be the pronunciation in here. Whatever. At a conceptual level, the graph Laplacian is the real space Laplacian used in quantum mechanics for the kinetic energy, generalized to generic and discrete graphs. Okay, let's let that sink. At a conceptual level, the graph Laplacian is the real space Laplacian used in quantum mechanics for the kinetic energy, generalized to generic and discrete graphs. In particular, for optimization problems, we can consider them as evolving under potential and kinetic energy defined by T equals Lg and V equals f of x. And why is this a projection of what? So those are basis states? I don't understand that. I don't understand that. So the Laplacian for a scalar function is a scalar differential operator defined by... Okay. Nope. Too complicated. Laplacian matrix. In mathematical graph theory, the Laplacian matrix is also called a graph Laplacian. It's a matrix representation of a graph. The Laplacian matrix can be used to find many useful properties of a graph. So G with n vertices, then it's a matrix with L n by n, where D is the degree matrix and A is the adjacency matrix. Okay, so it's D minus A. So what is the degree matrix and the adjacency matrix? I know. So this is just kind of flagging what elements are adjacent. So I find a graph. Yeah, it's a 0, 1 matrix exactly. Yeah. Coordinates are 1, 6. Okay. Oh, there it is. So, where was I? In the degree matrix, it's a diagonal matrix which contains information about the degree of each vertex. That is the number of edges attached to each vertex. Okay. And so the graph Laplacian is basically a one-dimensional set of points connected in a line is related to the kinetic energy of a system. And evolution and this operator generates the dynamics of the system in position or computational basis state space. While there are few formal definitions in the literature, the graph Laplacian will take the Lg of a graph G for an undirected K-regular graph as G minus AG. That's what I just read. So where dg energy are the n by n degree and adjacency matrices, the graph G, dg is a diagonal matrix. It's everything written here. I didn't even need to call that. The number of connections to that node or degree, and AG with entries equals 1 if nodes I and J are adjacent and 0 otherwise. Why that particular formulation though? Okay, so basically this is because the number of connections to that node. So this is because if it's got like, I guess what you want to do is if it's got these things here, 1, 2, 3, right? So edges, and then this is the degree. If minus the adjacency matrix, then it's basically 2. So that turns into 2 because it's 1 is adjacent to itself, right? And so you want to kind of ignore these. So by doing that, you're getting rid of the loops or the self-connecting edges. The degree matrix DG is proportional to the identity, and hence for quantum evolution, it may be disregarded as imparting global phase. Okay. But I'm still missing the connection here between these and qubits and these being an operator. Graph Laplacians have the important property that for connected graphs, there's a unique ground state with eigenvalue 0, which corresponds to the superposition. Interesting. Have the important property that for connected graphs, there is a unique ground state with eigenvalue 0, which corresponds to the plus state. Conceptually, this is the minimum kinetic energy state for all connected graphs. How is that so? And hence, any application of the adiabatic principle for finding the ground state starts with a state. With this state is the state minimum kinetic energy state for all connected graphs. So this implies that any connected graph G could in principle enable a meaningful quantum annealing schedule. So this begs the question of why one would choose one graph over the other. The study of continuous time quantum walks informs this question in the generic sense, but it's also clear that the precise coherences will depend on details of the matching between the node values, potential, and the underlying graph. One could imagine that a good match between the graph and the potential may yield good performance, or an open gap, while a poor one could result in the closing gap in the language of adiabatic quantum computation. It's these types of correspondences we examine, but we will not restrict ourselves to the adiabatic regime. I'm not sure I grasp that, like that part here with the eigenstate stuff, right? So the nodes are the computational states. So what is first connected? What is a connected? Is it a connected graph like an all-connected graph? Or what's that? Connected graph definition. A connected graph is a graph in which it's possible to get from every vertex in the graph to every other vertex through a series of edges. Called the path. Okay, so it means that everything's connected. It means you don't have like some sort of isolated graph. I get it. But then what's the mapping? Like what's the mapping between the Laplacian graph and an operator? These I don't understand. The nodes are computational bit strings, but what are the edges? No, that's already the max cap problem. So, kinetic energy cannot be ignored. What is this? Finite phase proposition. To isolate the wave function in bitstring space or surface area of the graph, the higher the kinetic energy is simply for the reason that it has one cat. The reason one has cat the graph. Moreover, for that number of cats on the nation face. What do these edges mean, though? if the nodes are computational basis states, what would these things mean? Where was I? Where was I? I definitely went too up, too down, sorry. So, a unique ground state with eigenvalue 0. So what does it mean to think of that as an operator? So you have nodes being computational basis states, and you have edges between those nodes, which mean what? Like they're not directed. So what does it mean? Are those maybe somewhat related to superpositions? And the lack of edges is somewhat entanglement, as in like those are kind of two disconnected possible branches. Conceptually, I don't understand that. Graph Laplacians have the important property that for connected graphs, there's a unique ground state with eigenvalue 0, which corresponds to the state. So how do you... How? How? But if it's an operator, there cannot be... Considers a energy state for all connected graphs, and hence any application. What is the energy state of these graphs? Study. Okay, let's move on. Maybe there's a bit of a better explanation later. In these above examples, we saw the two most common choices of bitstring graphs in quantum computing, namely the hypercube graph, which connects each bitstring to all neighbors one bit flip away, and the complete graph, which connects all bitstrings to all other bitstrings. These two graphs are special cases of a type of graph we'll find particularly compelling to analyze, which was called fast-forwardable graphs. In slight contrast to recent definitions of the fast-forwardable graphs, we mean that the evolution under the graph Laplacian can be done with a straightforward circuit implementation scaling upwards log t in the number of gates. This is the case for any graph Laplacian that has a simple quantum diagonalization circuit. For example, the Hadamard transform on all qubits, which diagonalizes both p plus and sums over tensor products of x terms. This also includes the Euclidean families of graphs and the meeting has been noted in the early works on quantum walks. It also includes graph defined as a primary picture. So maybe let's try to understand that. Graph Laplacians as quantum states. As quantum state density matrices. Yeah, but that brings me again to what the heck is a density matrix? In their entanglement properties. The peculiarities of quantum physics, blah blah blah. Entanglement in quantum mechanics. What is entanglement? Quantum states. A pure state can describe a state vector. In matrix algebra terms, the Brown notation is identified with a row vector, a column vector. A mixture of pure states is a mixed state. A mixed state can be viewed as a mixture of number of pure states and a sample of pure states. Mixed state can be represented as a state vector. So that's the density matrix is a mixed state. So it means we don't know which state really this is. So the density matrix formulation of quantum mechanics. the state of quantum mechanical system is associated with density matrix, a complex matrix A that is Hermitian, is positive, trace. This formulation allows for mixed states to be described as a weighted sum of pure states. Tensor product, into state vectors, the commutative system is described as tensor product. The qubit is described as a two-dimensional complex vector. Chronic product, density matrix formulation, separability, and entanglement. We say a density matrix for order and PQ is bipartite separable if it can be written as these. Is bipartite entangled if it is not bipartite separable. Is NP hard? Simple entanglement and separability, partial transpose. Decompose the density matrix into P square. So matrices for the Q. Okay, so Laplacian matrices of graphs. The Laplacian matrix of graphs is defined as D minus A, where D is a diagonal matrix of vertex degrees and A is the adjacency matrix. It's crazy how you can get lost into these really quickly. A graph's product Laplacian matrix is singular, positive, semi-definite. All eigenvalues are non-negative, symmetric. Trace is positive for non-empty graphs. This means that a Laplacian matrix with its trace normalized to 1 can be considered as a density matrix. Okay. Okay, so what it means is that it's interesting. So it means that this Laplacian graph, it's a way to describe a state as in like a not pure state, or pure state as well, right? In 2006, Braunstein et al. First considered Laplacian matrices of graph as density matrices and studied the relationship between the graph and the corresponding quantum mechanical state expressed by the density matrix. So you have the graph, you have the Laplacian matrix, you have the density matrix, and the state of a quantum system. Partial transpose graph. Arrange vertices on a P by Q grid. Each vertex has a label UV. The partial transpose graph has the same vertex set, and there is an edge of the partial transpose graph if and only if. Okay, but what does? It is easy to show that the adjacency matrix of partial transpose graph is partial transpose of adjacency matrix. Graph isomorphism. Separability is not invariant and the graph isomorphism. Vertex labeling is important. The complete graph is separable under all vertex labelings. The star graph is entangled under all vertex labelings. The Peterson graph is separable or entangled depending on the vertex labeling. Interesting. Okay, so so this is a way. So I think it's maybe a graphical or an interesting way to see whether there's entanglement or not. But still, what's the meaning of the damages? Okay, which kind of means, like, yeah, at the end of the day, it's like, what's the meaning of the off-diagonal elements of a density matrix? That's really what it is, right? Like, because that's how you make the mapping. And those are actually all these. I remember well. Those are all these relationships, like the correlations, not entanglement, just correlations. But correlations between effect of graph operations on separability. maybe we should play with some of these. Okay, so it basically means so the graph Laplacian is a way that we is something that can be mapped to a density matrix. And if the graph has no edges, that's equivalent. I don't know. What's the way to conceptually this is kinetic energy for all the connected graphs, and hence the application of the adiabatic principle. Where was I? The hypercube graph, which connects each bit string to all neighbors with one bit flip away, and the complete graph. But it's still, this seems to be somewhat used as an operator. I don't know. The connection Laplacian. Okay. Whatever, let's go on. The connection of Laplacians to kinetic energy with the current conventions will be important for developing understanding in this work. In classical random walks or searches over the bit strings in function f of z, the fact that walkers in any given instance of time are localized to single bit strings is relatively unimportant. However, in quantum evolutions, the global graph of the problem imparts a kinetic energy that can generate evolution unrelated to the problem fz from simply confining the wave function to a smaller support of bit strings. This force acts against us in quantum optimization in a fundamental way and can be influenced by the phase as well as with the unique zero kinetic energy state being the uniform phase, uniform white state. What? The global graph of the problem imparts a kinetic energy that can generate evolutions related to or unrelated to the problem. So so somewhat it seems this is implying that because maybe of entanglement or quantum correlations, that these somewhat affects like the random walks, right, or affects optimization. That these correlations really affect the optimization. But almost like as if it would just hinder the optimization because it's like they're pulling you towards one place or another because there are correlations between states, so you can't just easily walk randomly, right? That's maybe what they mean, or what it's meant here by this kinetic energy. Entanglement kinetic energy. How are those related? Are those related? So we discuss the average kinetic energy of an n non-interacting quantum particles and its dependence on n. For a peculiar entangled state, kinetic energy increases quadratically with n in contrast to its behavior in simple thermodynamics. That's what I thought. Like it seems like the entanglement somewhat increases that kinetic energy, which kind of makes it then intuitively seems like that's where this is going. That because of entanglement, that entanglement is actually hurting the optimization, or at least hurting random approach to the optimization problem. Seems to be kind of forming a bit of a more coherent image in my mind, but I'm not yet there. I think I'm not fully there. And that still kind of wakes it wakes up a bit the problem again of these non-diagonal off-diagonal elements of the density matrix, and what do they really mean? Like, how is the density matrix? How is that non-pure or that mixture? Like this, I think refresh that a little bit. And so this seems to basically say that this kind of state has zero kinetic energy because it's basically an equal superposition, and you can just move everywhere. Like there's no entanglement in there. There's just literally no entanglement. I guess the minus would be the same. We could try that. We could try checking the eigenvalues of these, but so hence if one can not use phase coherence to their advantage, the growing random quantum diffusion imparted from the kinetic energy operators are likely to act as a hindrance rather than aid. Interesting. Okay, I'll stop here. I need to let that sink a little bit. Definitely.